In the wild, the most lethal snakes usually rely on specialized chemical weapons to secure a kill. The gaboon viper is a prime example. This diagram shows how it uses 5-centimeter fangs to deliver a massive payload of venom, taking down targets with chemical efficiency. But if you examine a python, that chemical toolkit is missing. They produce no venom at all. They also face a significant structural deficit. They have no limbs to chase down, grab, or pin a struggling target. On paper, the python's lack of toxins and limbs makes it a biological underdog, seemingly disadvantaged for hunting large, powerful prey. Yet certain python species grow to 30 feet and routinely consume massive, agile mammals like wild pigs and deer. The python compensates for these deficits with a biomechanical toolkit. To understand how this limbless machine operates, we have to deconstruct its biological engineering through the exact chronology of a single ambush. In a dark jungle, the python waits motionless. Its complex geometric skin patterns provide camouflage that allows it to disappear into the leaf litter. Ambush hunting at night presents a mechanical problem. Standard vision is ineffective for spotting approaching targets in low light conditions. The anatomical solution is a row of specialized heat-sensing pits located along the python's upper lip. These pits detect thermal radiation emitted by the body heat of warm-blooded mammals. The snake's brain processes this data into a spatial targeting overlay, allowing it to see its prey regardless of ambient light. This sensory adaptation removes the need to expend energy searching for prey, turning a blind wait into a precise targeting system. The millisecond a target enters the strike zone, the python launches its entire body mass forward with its jaws unhinged. Inside the mouth is a geometric adaptation, rows of sharp, backward-facing teeth. This angle creates a mechanical advantage. It works like a fishhook, where pulling away only forces the teeth deeper into the tissue. This specific dental geometry anchors the snake to the target, solving the problem of not having arms to hold a struggling animal. Once anchored, the python rapidly wraps its muscular body around the prey. It is a common misconception that constriction kills by breaking bones or merely suffocating the lungs. The actual lethal mechanism is immense, targeted pressure that stops blood flow, leading to rapid circulatory arrest. The python uses a sensory feedback loop to detect the prey's exhalations, ratcheting its coils tighter into the newly available space every time the prey breathes out. This method of circulatory shutdown is energy efficient, incapacitating large mammals in a fraction of the time suffocation would take. With the struggle over, the python faces a final physical boundary. The prey is often visibly wider than the snake's own body. To consume it, the snake relies on the structural flexibility of its skull, specifically the lack of a rigid chin bone connecting the lower jaws. The python walks its mouth over the prey by moving these independent jaw sections to pull its body forward over the mass. Ultra-elastic skin accommodates this volumetric expansion, stretching to multiple times its resting diameter without tearing. Overcoming this physical boundary allows the python to extract the maximum possible calories from a single successful hunt. Now fully engorged, the python enters a phase of intense, prolonged digestion. Because of its low baseline metabolism, the snake hoards these calories rather than burning them immediately. This creates a unique timeline where one large meal can sustain the snake for many months. This entire process reflects a system of evolutionary economics. Every biological feature, from thermal targeting to independent jaws, functions to maximize the probability that when the python spends its energy to strike, that expenditure pays off.